Okay, folks, how we doing out there? Mr. Berto back with another instructional video. No music to open up this one because my wife has been doing YouTube videos as well, and she had a couple removed because of the music she put in the beginning. So now I'm afraid to actually put music in the beginning of these videos because I don't want them to actually get removed and then have to redo the video. Anyway, I hope everybody had a great holiday weekend. Okay, it's Monday here. I'm continuing with optimization. So all we're going to do today is talk about the homework problems and then talk about another way to solve these types of problems, because we spoke about solving them without the use of any calculator on last week on Wednesday, I believe it was. Thursday and Friday, you just had practice problems. So that's the calculus solution. There's actually a way to solve these problems with the calculator. So if you just take a look at the homework, this is from Wednesday night right here. What is the smallest perimeter for a rectangle of area, 16 square inches? Remember the process, okay? The first thing you want to do is find out what to maximize and minimize. We want to minimize perimeter. Looks like that was kind of cut off right there by the copy machine. So we want to minimize perimeter, and that means we got to get an equation for that thing, all right? Or in your best American Italian, I got to get an equation for that thing, all right? So an equation for perimeter of this rectangle, we'll just say the dimensions are x by y, which is actually going to change in other problems. It's a little bit better to put a B and an H there instead, because the calculator, you're going to see the issues that comes up when you're actually using an X and a Y. Anyway, so get an equation for that thing. So perimeter is just going to be 2X plus 2Y. Then you got to get it down to one variable and get a domain. They just can't say what's the minimum perimeter of any rectangle because it'd be 0, okay? You know, just make a rectangle. It's one single point. Technically, it's not really a rectangle, but the perimeter would be 0. You know, there's going to be some kind of restriction. There's a restriction here. They're telling you the area is 16 square inches. That means if you do dimension times dimension, you're going to get your area back. Okay, so area is x times y, 16 is x times y. You can actually solve for x or for y here. It's really up to you. We're usually so ingrained to solve for y, that's what I end up doing. So then we actually took out the y right here, replaced it with a 16 over x, and usually you want to write it in this form right here if you're going to take a derivative, okay? So find out what to maximize or minimize, get an equation for that thing, get a domain, okay? X here, the domain usually is going to be whatever your independent variable is greater than 0, or that's certainly a place to start, because X represents this distance right here, okay? And this distance cannot be 0. Well, in this case, technically it can't, right? Because if X is equal to 0, then Y is undefined. And the reason why is that you're insisting there has to be a surface here. You're insisting the area is 16. And if you're saying that your restriction is that the area is 16, there has to be a length and there has to be a width. One of them cannot equal 0. That's why there's no upper element here. You could try to set Y equal to 0 if you want to. If you set Y equal to 0, you end up with the equation 16 is equal to 0, which we know is not true, okay? So I know the domain bothers people. It really is useful when you're doing calculator problems like we're going to do today, but you can still get away with not having the perfect domain if you just put whatever letter it is greater than 0, then apply the first derivative test, the fourth part of our process right there. Let's take the derivative. You're supposed to see if it exists everywhere. You can see when you put the x downstairs, it's raised to the positive 2. This is non-existent when x is 0. And we already said x can't be equal to 0. It has to be greater than 0. Sometimes x can be included, 0 can be included in the value of x, but not this time, okay? If x is equal to 0, y is undefined. And once again, that's because you forced there to actually be a surface here. You said the area was 16, as opposed to like saying, a perimeter needs to be something, just a linear length. Then you could just have a length that's actually that amount, okay? Try not to worry so much about the domain. Take that derivative, set it equal to 0. I added 32 over x squared to both sides, okay? Solved here. Once you get x squared equals 16, you have to be happy, because we know that means that x is equal to 4 inches. But look, that's just a critical x value. That's the place where the perimeter function actually has a derivative that's equal to 0. So look, just because there's a horizontal tangent line in the function doesn't mean it's got to be a local max or a local min. It could be a local min, could be a local max, could be the increase and increasing. I did it backward, decreasing and decreasing, or increase and increasing thing. That's why we draw that P prime line, okay? And put that critical x value on the P prime line. Plug back into P prime, okay? See if you get a negative back or a positive back. And if P prime changes from negative to positive, that means the slope of the perimeter function changes from negative to positive, which means the perimeter function changes from decreasing to increasing, okay? So that's how I know that there's a min. I got to see that. Then you write up a little blurb that explains that line, right? We know the min perimeter occurs when x equals 4 inches. And make sure you answer the question appropriately. We had a practice problem, you know, I think where they just wanted to know the dimensions of like a rectangle of smallest perimeter. Here they actually want to know what's the smallest perimeter. So I actually took that 4, plugged it back in the perimeter function that only had x in it. If you want, you could get that y is also equal to 4, and then you could plug back into this perimeter function right here. Really up to you. And there's certain things I need to see. You know, some people just look at these problems, they can kind of work it out because they're simple types of situations. Look, I need to see that formula for what you want to maximize and minimize in one variable with a domain. You could start right there if you want to, if you're good enough, but I need to see something like that. If it's a calculus solution, which is what this is, we'll talk about a calculator solution in a minute. I need to see that you're taking a derivative, and I need to see that you're setting it equal to 0. You know, if it happens to not be non-existent in x value, you don't need to say it's non-existent there if it's not in the domain. So usually we just worry about equal to 0 here. Then you got to solve this equation. You can go right to the answer if you want. I got no problem with that. You got to show the line because you're showing there's a max or a min there. You got to write a little blurb that explains the line. This line means there's a minimum when x equals 4 inches. Then you have to answer the question. So it's a little annoying with the amount of work that you have to show. If this will be a take-home assignment, something like that, I'm going to be looking for those things, okay? So just be careful. You could use your calculator to actually get what our solution is here, okay? If you want to go for a calculator solution, the first 3 steps of the process is still the same. Find out what to maximize or minimize, get an equation for that thing, get it down to one variable, and get a domain, okay? And the 4th thing that we did over here was we applied the first derivative test, use calculus to show where there's a max or a min. Here, we're just going to use the calculator, okay? So really the 4th step in the process for a calculator solution is going to be use the calculator. I'm not going to tell you on the assessment whether I want you to use a calculator or I don't want you to use the calculator. You know, you'll have the calculator at home anyway, but when you write up these calculator solutions, you got to do it in a way where it looks like you didn't have the calculator. And look, we're going to start right here. Here's our formula for perimeter. We know it's 2x in one variable plus, you could say 32x to the -1. I'll say 32 over x just for kicks and giggles. Here's my domain, x greater than 0. Okay, and here's the thing. A function always represents, very good, y values, okay? So the y values of this function represent perimeters, okay? We just want the minimum y value of the perimeter function, which means we're not going to take a derivative. We're going to sketch the perimeter function and hopefully see a minimum, calculate that minimum. But you got to make sure you label the axes here. This is going to be the x-axis, but this is not going to be the y-axis, okay? You know, y represents this distance right here. This formula, the y values represent perimeters. This is the perimeter axis, okay? Your calculator is going to say y equals. You got to know that y really represents p, not this y over here. Your calculator has no idea that you called this distance y right here. We're starting with this formula that's only in terms of x. That's why you want to stay away from x and y on the graphing calculator. We'll talk about that more. But now I could just graph this thing, okay? And it's not as easy as you might think, especially with a min. It gets really annoying, okay? But if we go to y equals over here, okay, you know we have 2x, okay, Twix, the only candy bar with the, very good, Cookie Crunch, plus a little alpha y equals, fish equals here, 32 divided by x. You know, and the other thing is when you actually want to graph this thing, is people are like, yeah, I'll just zoom 4. That's what Berto said to do. And then you zoom 4, and you can see it's thinking right here. What is it doing? I have no idea because I don't see anything, but I know it's still actually working. Oh, so I didn't see anything. So let me go to zoom 6 because Berto said don't use zoom 6, but it always worked for me. I'm just going to go for zoom 6. And you can see it looks like we're getting nothing for zoom 6 here as well. You got to be intelligent. These numbers are a lot bigger, maybe not so much in this problem, but certainly in the next problem than a lot of problems that we're used to dealing with. So really, you might actually remember zoom fit. Zoom fit is a great technique. The only problem with zoom fit is that you need to have a domain established first. We usually try to get a domain in these problems. You know, the problem is if she came in through the bathroom window. Okay, you know, your domain, we know our x min is going to be 0, but I don't know what the max is going to be. Okay, so you got to kind of estimate, you know, or guesstimate a little bit here. You know, think about what x represents. Represents this distance right here. Okay, and I know if I multiply x by y, I'll get 16, which means x is probably something that's not really too big. It's not like 20,000 or something like that. We already know what x is. We know it's 4, but you want to pick something that's bigger than x, okay? So, you know, x times y is equal to 16. You know 16 is probably bigger than x, okay? Technically, you know, x could be something bigger than 16 if y is, you know, like 1/17 or something like that. But we won't worry so much about that. You know, if you put the 16 here, okay, and once you have that domain established, then you zoom 0. Let's see if we see a min. We're looking for a min here. So you can see the graph decreases, and then it does look like it starts to increase over here, okay? You know, if that's not good enough for you, maybe you're like, you know, I can't really see that min. You can go back into the window and adjust. Just go big or go home. Don't be like, I want to make it a little bit smaller. Let me make it 15. No, make it like, you know, half of this, like maybe 8, something like that. The problem is if you zoom 0 here, you'll see the decrease, but you're not going to actually see the increase for the minimum, okay? So when that happens, when you start picking, maybe you pick the upper element is 8, and you realize that doesn't work. Maybe like, let me go smaller. Let me go to 4, you know, zoom 0 that. Go big or go home. Try to at least go in halves or something. Don't go from 8 to 7. And you'll see it's just getting worse and worse here, okay? You can't actually see what the min is. So if you're moving in one direction and it's getting worse, try to move in that opposite direction. Remember, we had a 16 here. Okay, maybe you couldn't see it with the 16. Maybe you make it bigger, like 25 or something like that. Zoom 0. You know, and eventually you should see that min. Let's see how it is here. Pretty good, okay? The only thing you need to worry about is that right now it looks like the min, remember, this is the x-axis, this is the p-axis, represents perimeters. It looks like the min right here is right on the x-axis, which would mean the minimum perimeter is equal to 0. That's not true. The problem is when you use zoom fit, if you go back into the window, you'll see your y min here is positive 16. I don't want it to be positive 16 because then it's above the x-axis, right? I'm not going to be able to actually see, you know, the x-axis in it. So if you make the y min equal to 0, that's going to actually give you your x-axis. And don't hit zoom here. If you hit zoom 0 again, it's just going to take you back to the same graph we had before. When you voluntarily adjust the viewing window, that's when you hit graph. And now you can see my minimum right there. And you want to sketch it out, okay? And it does not need to be a perfect sketch at all, okay? In fact, you don't even need to worry about what's going on at the ends of the graph. Technically, there's a vertical asymptote here, right? It doesn't exist at x equals 0. But you just care about this point right here, the minimum point, and we're going to calculate that minimum. You know how to calculate a minimum on your calculator, okay? So a little bit to the left. Let's go. Bug, a bug, a bug, a bug, a bug. A little bit to the right. Okay, and let's have it guess. And there's our minimum. Take things with a grain of salt here. You could use 3-place accuracy. You could put 3.999999. Remember, that's really just a truncated version of 4, though. That's really supposed to be a 4 right there. And this right here is the 16. And this is what freaks everybody out. They're like, oh, x equals 4, which we got before, right? X equal to 4. Then they're like, oh, y equals 16. So this y must be 16 right here. No, okay, remember when we put this in y equals, this is my perimeter function. This is p equals. So from now on, when the calculator spits back a y to you, he really means a p. That's who he put in his spot. I got to calculate this again. Well, I shouldn't even have to do that, actually. We have the graph. It's calculated right here. So this 4 right here does represent an x value. But that's 16 right there. He represents a p-value. That's the minimum perimeter. Okay, you can see the perimeters right here getting smaller and smaller and smaller until they bottom out right there. Then they get bigger and bigger and bigger. So now you could just actually answer the question, what's the smallest perimeter? It's right there. We know the min perimeter, we know is going to be equal to 16. And my units here would be inches. You don't have to write out a blurb or anything like that. You know, in fact, when you want to do a calculator solution, I got to see the formula for which you want to maximize or minimize in one variable only. And I need to see a domain, just like here. Only now, don't take the derivative, okay? Put it in the calculator. I need to see a sketch. And you better label those axes, okay? Otherwise, I don't know what the heck the sketch is representing. Make sure you also calculate the max or the min point. Then you could usually go right into answering the question, okay? You know, be careful with a min, because if you zoom fit, which you're probably going to want to do in most of these problems, you're going to have to adjust that viewing window, okay? So you always want to make that, you know, y min equal to 0, so you can actually see the x-axis. So that's really what the deal is today. You know, we got a function whose y values represented perimeters. Instead of using calculus to find the min, you could use the calculator to find the min. They don't really have you do these things on the AP anymore, but it's important, sorry about that noise, it's important to see the connection between the calculator solution and the calculus solution. And it's important to know when to do which, okay? When I tell you to do a calculator solution, please do a calculator solution. Make sure you show the appropriate work. This one should be easier. Just like the problem we did yesterday, we got a field, a rectangular field adjacent to a river, and you're only going to have fencing on 3 sides of the field right here. 1,600 feet of fencing, so 2b plus h is equal to 16. I use b and h. You might have x and y. It might not be so easy to check your work, but you'll see b and h helps with the calculator, because like I said over here with the calculator, it says y equals 16. People think that represents this y over here. Your calculator is not looking at your paper like, oh, what'd you make y equal to over here? He's not doing that. He has no idea what y is. You put p in y's spot. He thinks that's what y is, perimeter. So be careful. You know, over here, maximize that area. Area is going to be b times h. Let's get it in terms of one variable. You could solve for b or solve for h. It's really up to you. It's just easier to solve for h. Make your life easier for you in these problems. It's going to help out in the long run. My domain, hopefully not too terribly. You know, you knew the lower element of the domain was going to be 0. Domain here in terms of b, right? That's my independent variable. B could actually equal 0. If b equals 0, it just means h equals 1,600, which means you're just going to have one vertical line equaling out to 1,600 feet of fencing. Doesn't give you a rectangle though, okay? So certainly it's not maximum area. That would be minimum area. So you don't need to include that 0. Where'd the 800 come from? Well, the 800 is the value of b that makes the other letter equal to 0. Just take the other letter and set it equal to 0. Here's h. We don't want him to equal 0 either. And you'll see if you solve this equation right here, you'll end up with b equal to 800. So here's the value of b that makes b equal to 0. Obviously 0, and here's the value of b that makes h equal to 0. That's where the upper element comes from. You could still do this without the upper element, right? Take the derivative, set it equal to 0, solve. You could have an arrow over here if you want. You don't need to have that 800, but man, is it really going to help when you use the calculator, okay? By the way, make sure you take the derivative, okay? Set it equal to 0, you solve. You show me that line, you draw that blurb, right? You know, what does that mean, this line? It means the area is a max when A is equal to, B is equal to 400 feet. I got what H was equal to just so to find that max area. Oh, sorry, we don't want max area, right? We want the dimensions of the field of max area. So I knew B was 400. The other dimension is H, so I plugged that in right over here, B equal to 400, and I was able to solve for what H was. They never wanted that maximum area, so be careful. Make sure you answer the question. You know, calculator solution, you still want to get an equation for what you want to maximize or minimize down to one variable. And you want to get that domain, so we're going to be right here. So the first 3 steps are the same, but don't be taking a derivative. Now I'm going to figure out where this thing has a maximum by actually sketching the area function, and it should look like a max, all right, something like that. It's a little bit easier, this one right here. Let's use that calculator. You know, certainly the numbers are a lot bigger. I'm putting this in y equals right now. Remember, it's really a equals. So anytime the calculator spits back a y to me, that really represents area. And I can't use b in the calculator. I'm going to use x. You always use x for the independent variable. So that means that x really represents b. So when the calculator kicks an x back to me, he really means this distance, this b right here. So you got to be careful with that when you're using the calculator. She came in through the bathroom window. I know the domain here, 0 to 800. These numbers are really big. If you didn't have that upper element of the domain, it would make things a little bit more annoying. But once again, you could guesstimate a little bit. You know, if 2 times b plus h is 1,600. Remember, we want to find a number that's bigger than b, okay, because we want to go out a little bit further over here. So, you know, b, if you want to think about what it has to be, you know, it's probably less than 1,600. But if you go out to 1,600, you'll probably get a decent graph as well. We don't have to do that because we went out to 800 here. Should be good enough. You got to play around if you don't have that domain. Now we zoom fit, right? Zoom 0. Only after you get what that domain is and put it in the calculator, it'll think about it. Maxes work out great because you don't have to worry about changing, you know, the y minimum to be able to see that x-axis, which in this case, by the way, is not the x-axis, it's the b-axis. Make sure you label that. Make sure you label this as the a-axis. So mins are a little bit more difficult to get that graph. Maxes tend to be a little bit better. Let's calculate that max. A little bit to the right over here. Okay, and you can see that this should be 400. Take it with a grain of salt. Not too much salt. Remember, heart disease, very dangerous these days in America. Comma, what is that? 320,000, I think. Remember dates I have this weekend. It's a joke, okay? 320,000, I think that's what that says. You know, and think about it. Now let's answer the question, right? They want to know what the dimensions of the field are going to be. Remember, this 400, that's a b value, right? This 320,000, why is it so big? That represents A. That's actually the maximum area. They didn't ask us about that here. You know, here I'm just going to say, hey, I know that we have max area when, and I know it's when B is equal to 400 feet. And I could easily get what H is equal to by plugging back in, just like I did over here, getting 800 feet. All right, so you don't need to write up as many blurbs. You know, remember, calculus solution, need to see a formula for what to maximize and minimize in one variable with a domain. Then with the calculus solution, you got to take that derivative, set it equal to 0, solve, and draw the line. And then write that blurb that says what the line means. This line means you have maximum area when B is 400 feet. Then you want to answer the question. Here they wanted the dimensions, so one little extra step there. With a calculator solution, okay, you have to still get the formula for what you want to maximize and minimize in one variable, get a domain. You got to sketch a graph and label those axes. If you don't label them, I have no idea what's being graphed. You got to calculate that maximum or that minimum point. You don't need to write that this means B and this means A, but it could be helpful. And after that, you could usually go right to solving, you know, the problem, answering the question. And look, we're going to do different types of problems coming up this week, but essentially these are the only two types of solutions you're going to have to worry about. So please try your homework tonight. Pretty sure one of the homework problems is a calculus solution. One of them is a calculator solution. You know, so see how that goes. Make sure you use the appropriate solution. Also, make sure you got that take-home for me today. Hopefully it wasn't too terrible. You know, it was open notebook, obviously. It was just like basically the test I was giving class anyway. So you have a severe advantage there. Make sure you take advantage of it, okay? It's the last grade of the third quarter. And we'll be back here tomorrow doing more maximizing and minimizing, all right? So take it easy, everybody. Stay healthy. Stay safe. Adios.